Hi, and welcome to 4.2 Newton's second law. In this lesson, students will be able to explain Newton's second law, and students will be able to use Newton's second law to calculate the force acting on an object, its mass, and or its acceleration. So I made some little crazy animations to kind of lead into what Newton's second law is all about. So let's think about acceleration and force. Well, you have a little kitten, and the kitten has a little kitten toy, and it's going to exert a force on the toy. It's going to push it. That little kitten is not very strong, so when it pushes it, the toy doesn't accelerate very much. Meow. Kind of just looks like that. So instead of a kitten, let's say we have a tiger, because we are the tigers, the White Plains Tigers. So you want to have this big, strong tiger that is capable of exerting a greater force, but you want to keep the mass the same. And compared to the acceleration that the kitten can produce, what do you think the acceleration that the tiger can produce is? Roar! So the greater the force, the greater the acceleration, right? If you push on something harder, you can accelerate it more. Double the force, double the acceleration. If you multiply the force by 10, the acceleration also multiplies by 10. And if you exert less force, if it's half the force, it's half the acceleration. So what kind of relationship do you think exists between acceleration and force? All right, so that's not the full picture, though. You also have to take into account the mass of the object when thinking about its acceleration. So you can push on this big, heavy truck with a great amount of force, but is it going to really accelerate that much? Maybe not, because it's so massive. That truck is so massive. Now, let's say you take the same, oh, I'm pushing really hard, same force, and you exert it on a truck that's a little smaller, like that little kid in the little toy car. If you push that toy car really hard, just as hard as you would on that big truck, which one is it going to accelerate more? The less massive car will accelerate more. So if there's less mass, there's more acceleration. All right, so we're keeping the force the same in this analogy. And if we double the mass, if it becomes more massive and we keep the same force, there's going to be half the acceleration. And if it's 10 times the mass, very massive, you're not going to accelerate very much at all. And if it's half the mass, then you can get double the acceleration given the same amount of force. So what kind of relationship is that? Is that the same type of relationship between acceleration and mass and acceleration and force? Hmm. Well, we said that basically the greater the force, the greater the acceleration, and the greater the mass, the less acceleration you'll get. So what kind of relationship exists between these two, really three variables? Force is directly proportional to acceleration, because if one goes up, the other goes up. And mass is inversely proportional to acceleration. So if the mass goes up, the acceleration goes down. Very interesting. You know who else was really interested in this? Sir Isaac Newton. He saw this relationship and he said, sweet. So he came up with Newton's second law. Now, Newton's second law, the definition it doesn't roll off the tongue like Newton's first law, an object at rest stays at rest, and an object in motion stays in motion with constant velocity in a straight line, unless acted upon by a net force. I mean, I guess it rolls off the tongue. Newton's second law, though, I don't know, it's going to be hard to remember this. It says the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. I wish there was like an easier way to remember Newton's second law. I wonder, we're talking about these relationships, direct and inverse. I wonder if you had to make an equation that had F for force, M for mass, and A for acceleration. And you wanted to make sure the force and the acceleration was directly proportional, and the mass and the acceleration was inversely proportional. What would that equation look like with those three variables? Think about it. Pause the video. Take a think. Take a little thinking break there. All right, did you think? Let's see. This is Newton's second law. A is equal to F over m, otherwise known as F equals ma. Or some people write nowadays F equals AM for fam, but that is an abomination. No, I mean, if that works, that's fine. Normally, I learned it F equals MA, but now there's this fam thing running around. All right, so a couple things to note. This is the net force. We didn't really talk too much about net force yet. That's going to be in the next lesson where we'll actually calculate the net force. For now, we're just going to do problems pretty much where there's only one force. So you don't need to find the net force because there's only one force acting on it. When there becomes multiple forces, then you'll have to find the net force first. But we're just breaking it down here. All right, so then why does it look like this? The acceleration and the net force are directly proportional. If I double the force, I put a 2 in the numerator, I'm going to have to double the acceleration in order to balance the equation. And then the acceleration and mass are inversely proportional. If I double the mass, I put a 2 in the denominator, so I have to do the same thing on this side of the equation to make sure that the equation is still valid. So this is really the definition of Newton's second law, but a lot of times people just remember F equals ma. So either way it works. I wonder which version is given to you in your reference table. Take a look in your reference table and see if you could find Newton's second law. You could pause the video here, make sure you take out your reference table and try to find it on your own before I show you so that you can remember it better. Okay, so we are in the mechanics unit still. We're in dynamics, which is a subunit of mechanics. We started with kinematics, now we're doing dynamics, but it's still mechanics. And Newton's second law is right underneath all that other stuff we learned. And they have this version of Newton's second law there. Let's see, there's also over here, it looks very similar. Okay, we're going to do a lesson called mass and weight, where we'll break that equation. But it's pretty much the same thing. Instead of acceleration, you have acceleration due to gravity. And instead of the net force, you have the force due to gravity. And all of these things can be found on the right side. Don't forget, it's in alphabetical order for your convenience. All right, but right now we're just talking about this. Okay. So a couple things to point out. Is force a vector or a scalar, and why? What do you think? Is force a vector or a scalar? We talked about it yesterday. Force is a vector because acceleration is a vector. It has a direction. You can accelerate in different directions. And in our equation, we can see, oh, there's the vector over there. Force is a vector because I could push something in different directions. Therefore, it must be a vector because it has a magnitude. I could change the size of the force and a direction. I could change the direction of the force. And then this will come up, how can we rewrite newtons in terms of meters, seconds, and kilograms? Because don't forget, we talked about forces yesterday, and what is the unit for force? The unit for force is this guy, a newton, with a capital N because that's his name. Don't make it a lowercase n. That is disrespectful to Sir Isaac Newton. So you want a capital N, not for an angle or anything like that, but a capital N, all right, for Newton. And then what are the units for mass? What do you think? Do you remember? I guess the last time we talked about it was the SI base units thing. Do you remember mass? Is it grams? No, no, no. It's going to be kilograms. And then acceleration? Meters per second squared, like that. Okay, so if instead of newtons, you wanted to say, ooh, I pushed that object with instead of 5 newtons, you could say 5 kilogram times meters per second squared. If you wanted to be a really big nerd, you could definitely say that. Or you could even write it like this. Ooh, kilogram meter per second squared. That's fine. when we're doing our equations, we're going to use Newton's. Why am I showing you this? This is going to be a great multiple choice question saying, pretty much which unit is a valid unit for force or something like that. And they wouldn't give you a Newton. They would give you like kilogram meters per second, kilogram seconds squared per meter. And then you'd have to pick out that this is the right answer because, again, it's mass times acceleration. Mass times acceleration. Okay. So another thing that we could talk about is Galileo's experiment. All right, so we started Unit 3 talking about free fall, and I dropped a shot put and a croquet ball, and then I dropped even a shot put and a crumpled up piece of paper, and they both dropped at the same rate. And Galileo is said to have done this from the Leaning Tower of Pisa. Did he? Some people say no, but it's still a good thought experiment, and it's a good point to make here. So let's talk about it. He has two different sized balls, so two different masses, and he drops them at the same time. Do they hit at the same time? Do they accelerate at the same time? Let's see. So here's the experiment, right? And we kind of just brushed over this before, but now that we know Newton's second law, we can really explain why, okay? Why do they accelerate at the same rate? For both of these 1 kilogram and 10 kilogram balls, they're accelerating downward at the same rate. Why? It comes back to Newton's second law. So think about the mass of this ball compared to the mass of this ball. This mass is much smaller. All right. So when we plug in, this is only 1, this is going to be 10. When we plug it in our formula, this mass is going to be smaller. Well, tell me about the force that's acting on that mass. If you were holding both of these, all right, which one is exerting a greater downward force on you? This is the force due to gravity. Which one has a larger force? The 10 kilogram one has a larger force, and the 1 kilogram one has a smaller force. So not only does the 1 kilogram mass have a smaller mass, it also has a smaller force. It feels lighter. So it looks like this. They both decrease at the same rate. And you get the same ratio. And you could increase this mass. So this mass is bigger, but as you increase the mass, the force due to gravity is also bigger. And those two variables change at the same time. So when you do the actual division, you still get the same number because it's almost like a ratio. And that number, of course, is negative 9.8 meters per second squared on the surface of Earth. And we could even say from before, well, the force, we said it's a kilogram meter per second squared, and the mass is measured in kilogram, right? So these kilograms cancel out, and that's why you're left with meters per second squared there. Fun stuff. So now you kind of have the better picture of why they accelerate at the same rate. It comes to Newton's second law. Okay, so this is what a problem might be like on your homework or a test or a quiz. I wanted to use tigers again. So it says a 2.5 kilogram cat toy is at rest on a horizontal frictionless surface. A tiger swats at the toy and accelerates it at a rate of 15 meters per second squared. With what force does the tiger hit the toy? And then I had some fun with these pictures because they looked pretty like you could see the emotion on the cat's face there. Okay, so I would do the guess method. It says the mass is 2.5 kilograms. Okay, the acceleration of the toy is 15 meters per second squared. Is it on Earth? Does it have an acceleration due to gravity of negative 9.8 meters per second squared? Yeah, but we're not going to use that in our equation. Here's why. Here's the cat toy. The force we can think of as being exerted to the right. This is the force because it's accelerating to the right, positive. 15 meters per second squared. Okay, see how both these arrows, we're just looking at the rightward direction right now. We're not analyzing anything about the force due to gravity or something called the normal force. We don't have to worry about that right now. Um, so we're just looking at this force. That's what they're asking for. And they tell you this acceleration. So you don't, because people like the 9.8 now, but remember, you don't always accelerate at 9.8. So don't overthink it. This one's just pretty straightforward, and we could even do F is equal to ma. And technically, you should write net force there. You don't have to. This also means net force sigma. All right, is the math symbol for sum. But for now, we could just do F equals ma. F is equal to 2.5 times 15. So the force is equal to 37.5. And what are the units for force? Newtons, capital N for my guy, Sir Isaac Newton. And don't forget kilograms for mass, not just grams, kilograms. All right, number 2, you push your lawnmower with a force of 25 newtons at an angle of 30 degrees below the horizontal. The lawnmower accelerates at a rate of 0.5 meters per second squared. And we can assume that you're not accelerating through the ground, you're accelerating to the right, across the ground. It says, what is the mass of the lawnmower? So you remember how I said don't overthink it? Now it's time to overthink it. Because in Newton's second law, it says that the force has to be in the same direction as the acceleration. So it says the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force and in the same direction as the force. The acceleration has to be in the same direction as the force. So let me ask you something. It says we want the force that acts in the same direction as the acceleration. You're pushing at this weird angle downward, but the lawnmower is accelerating to the right. So can we use the number that they gave you for this, or should we use a different number so that it's in the same direction as the acceleration? That's right. We're going to have to break this into components. All right, so which one of those components should we use? The x component. So we need to find fx first before we can use Newton's second law. You always want the force to be in the same direction as the acceleration, because that's the actual thing that's doing like the work, you could think of it. All right, it's the thing that's causing the acceleration. Just the x component is causing the acceleration. All right, so we can write, okay, so F is equal to 25 newtons. What else do they tell you? Theta is equal to 30 degrees, so that's going to remind us to find the component. A is equal to 0.5 meters per second squared. They're looking for the mass. The first thing that we have to do is break this 25 newtons into x and y components. We're looking for fx, this is 30 degrees. So therefore, and this is f. Therefore, fx is equal to f cosine theta. Oh, is it cosine? Oh no, it's 30 degrees below the horizontal. So that's really this angle. My bad. I'll draw the picture better. This is what it is. It says 30 degrees below the horizontal. So here's the horizontal, and that's the x component that we're looking for, which is why we can use cosine, because it is adjacent to that angle. So fx is equal to 25 cosine 30 degrees. And instead of 25 newtons, we're going to use 21.65. 21.7 is good enough, okay? So now we can use fx to find the acceleration. So you could just do F is equal to ma. 21.7 newtons is equal to, we're looking for the mass of this lawnmower. The acceleration is a half a meter per second squared. So we're going to double that, and it becomes 43.3 units for mass. What do you think? Units for mass? Kilograms. Okay. All right. Cool. One more problem here, bringing back kinematics. It says a 1,500 kilogram car is traveling with a speed of 20 meters per second. What is the magnitude of the horizontal net force that is required to bring the car to a halt in a distance of 35 meters? See if you could figure this one out on your own. Pause this one. This is a good review of things we've done in the past. Pause it. Okay, so here we go. This is the answer now. This is the situation. Your initial velocity is 20, your final velocity is 0, and you want to cover a distance of 35 meters. So if we wanted to use, then they're asking for the force, right? So we want to eventually use Newton's second law, but right now we only have VI is equal to 20, VF, it comes to a stop, so that's hidden information. All right, D is equal to 35 meters. And then they tell you the mass of the car, 1,500 kilograms. And they're looking for the force required to bring it to a stop. Well, I really want to do F equals ma to find the force, but I don't know what a is. So it's actually a two-step. The first thing we have to do is use a kinematic equation to find the acceleration, which you should know how to do. And the second step is to use that acceleration with Newton's second law. So if you want to pause the video now and work that out, you can. But I'll just write the equation. So we want the kinematic equation without time. Somebody said that this was the timeless equation. I agree, it is pretty timeless. And then you substitute in your values, and then you can solve. And you're actually going to get a negative number for this. You get negative 5.71 meters per second squared. Negative 5.71 meters per second squared. Doesn't make sense that we got a negative number. Yes, because even though your velocity is to the right, you're slowing down, so that means your acceleration must be to the left, and also the force that is slowing you down must be to the left. It's moving against your motion. Okay, so yeah, we're going to get a negative force as well when we do Newton's second law. So here it is. You substitute in your numbers, and you get a force that is negative because it's moving against the positive velocity. It's negative 8,571 newtons. If you wanted to use significant figures, it looks like it would be negative 8,600 newtons. So that's totally acceptable too. Whatever you want to do is fine when it comes to rounding like that. Really nearest tenth, that's pretty fine. Okay. That'll do it for today. Thanks for watching and have a great day.